All right, cadets, I've been getting a lot of questions about distributed loads. So I'm going to go ahead and try to explain that real quick. And I've actually got a live cadet here. Cadet June O is in the classroom with me. Well, it's not a classroom, it's actually my office. And we're going to go ahead and do it on this board right here. In general, when we have a distributed load, we mean a load which acts over some extent. A point load is a thing like a tire on a plane, right? But if you had the skid on the bottom of a helicopter, the skid on the bottom of the helicopter has some extent, and so might form a distributed load instead. And if we take a very general case, we have some force function that's acting on the top here. And we would be interested in resolving that force, resolving this distributed load where I have some, where my force is some function of x, meaning that the force that's acting downwards is changing as I go from left to right. And I'd like to resolve that into a single force acting at a single point in order to solve the reactions at my ends, here and here. Now, eventually we're going to talk about beams and bending, and we can't always reduce our distributed loads into a single force in those cases. But in the case where we're solving for moments and reactions, we can absolutely do so. And the key is that I need to find the force due to that load is equal to the area under the function. And that force, you're seeing my back here, that force acts through the centroid of that function. So I'm going to be able to take this whole blue function right here, which is acting downwards as a distributed load, and I'm going to be able to turn it into a single force acting through a single point. Let's take a super easy case. The super easy case might be a distributed load. Wait, I should use red chalk, right? Forces in nature are red. I might have a distributed load which is constant. And this might be, say, 4 inches of water acting on a warehouse roof, right? Wind blowing evenly against a surface, right? Each of those would cause a rectangular load of this kind acting downwards on a beam. So there's my beam. June, you with me so far?
Yes, sir.
Good. So this is going to have some magnitude, right? And that magnitude might be 600 pounds per foot of length of the beam. And let's say that my beam has some length of 15 feet. So the area under this simple function is going to be the height times the length, or 600 pounds per foot times 15 feet. And if I do that simple math, I'm going to get 9,000 pounds. Now the centroid of a rectangle is a pretty straightforward idea. The centroid of a rectangle lies right here. Then the force is acting downward through the centroid, and that means I can apply it to my object right at that centroid. So I'm going to take this distributed load, and I'm going to replace it on my free body diagram. Now you're going to draw a separate figure, right? I'm allowed to erase. I'm the professor. You got to draw a separate figure on your beautiful green engineering paper, and you're going to act right here. And what's the distance from the left-hand side to that point of action? Why, that's a simple 7.5 feet, because it's halfway across. Another question might be, hey, what about a triangle? A triangle is going to be handled much the same way. You'll forgive me if I erase here quickly. That triangle might increase from left to right, or right to left. And let's say that it had the same magnitude. It had a magnitude of 600 4,500 pounds per foot, and my beam was the same 15 feet long. That force is equal to the area under the load, would be the area of a triangle, or 1/2 15 feet times 600 pounds. What do we get then? I get 300 times 15. 300 times 15 is going to give me 300 times 15, 3,000, 4,500. Or exactly half of what I got in the rectangular case. Where is it acting downwards? The centroid of a triangle lies 1/3 of the distance from the fat end of the triangle. I'm going to say that again. The centroid of a triangle, and you can look in the back of Philpott for this, lies 1/3 of the distance from the fat end of the triangle. So I'll knock this triangle off of here, and I'm going to replace it with a force of 4,500 pounds. And where is it acting? It's acting 5 feet from the left-hand side. Now, a question that you might be wondering about in your current problem set is, what if I had a rectangle and a triangle? What would I do then? If you had a rectangle and a triangle, you could resolve each one of them separately and add them together to make the shape you were given. If you had a parabolic spandrel, I'll leave that to you. You can take a look in the back of Philpott, and he's going to lay out for you what a parabolic load might look like. So I can either take a rectangle, hey, it acts in the center and it's length times height. I can take a triangle, it acts at the 2/3 from the skinny end or 1/3 from the fat end, and it's 1/2 base times height. Or I can add a rectangle and a triangle together to get a single shape and solve it as, hey, I'll solve the rectangle first, the triangle second. I hope this helps to clarify distributed loads for you, and I hope you enjoy your continued exploration of the fabulous world of statics and mechanics.